Oui, bah oui, oui.
Faut commencer. Quelques minutes. Encore quelques minutes. Ouais, je tourne les barils.
Ah, c'est bon, c'est bon. Ah, oui. Elle est là?
Oui,
Il est donné ici, je crois. On va voir.
On le connaît.
C'est 4 secondes. L'horloge est tout à l'heure. Oui.
On va commencer. Il est là, tu l'as vu? Ah, il a 10 secondes de retard. Moi, ça fait 4 secondes de retard. Personne n'est là. Justement. Okay, so it's a great pleasure to have Sergei Nechaev with us. We all know Sergei, so little presentation. Sergei has been for 25 years our neighbor, now even closer neighbor in LPTMS. He's a specialist of statistical physics, many different aspects. I would say with some emphasis on some combinatorial aspects, in graph theory, in limit shapes, in knots, surfaces, and so on. So thanks very much for accepting our invitation.
Thanks a lot. Okay. I would like to say that this is the first time when I'm giving this kind of presentation, and many aspects of the topics I'm going to discuss are known, and maybe my contribution is just kind of links between them. And okay, so let us start, and I will go step by step, and probably the structure of the talk is like that. So I will start with kind of Dejean-like approach to scaling of straight random walk above convex surfaces. So then I go to trying to explain how this can be linked to renormalization group equations for random walk in Poincaré half space. So then another link from this to this will set the VKB, WKB approach to and a redistribution for again to rederive the KPZ type exponents, and then I will explore this connection, saying how this might be related to Lifshitz tails, large deviations, and also to Fibonacci sequences, allometric landscape, and some structure related to modular groups. Okay, so I don't know if I will succeed in explaining all these details, but let us go step by step, and let us start with this, I would say, maybe the most naive and most simple problem. So I start with the following question. So suppose that you have two-dimensional plane, you have surface which is shown, semicircle which is shown by gray shape, and the random walk which starts in point A and ends in point B, and this is just a standard random walk staying in upper half plane, no interactions, except that this random walk cannot go down and cannot enter into this gray area. So it's you can forget about volume interactions, just standard random walk. And the question we ask is the following. What would be the typical span of this random walk above the point O? Yes, so above this. For instance, you put the plate and you look what are the typical deviations of this random walk from the point O in the vertical direction. And in principle, one can set, there could be two different settings. One is like that. So it's not what is drawn here. It's basically, you can imagine, so that the situation is like that. So I mean, this bump, this surface is very small, yes, like that, and the random walk is very long. Yeah. So and typically the number of steps is of order or bigger than r squared, and r is the radius of this semicircle. Okay. So for simplicity, we stay on the lattice, and the spacing of the lattice is equal to 1. So I count everything in number of steps. Okay, so in this case, of course, you can get nothing else as just a diffusive type of behavior. So d small is the same as d capital. Yeah. But now let us go to the opposite limit. Let us say that our trajectory is stretched. So it means that the length of the trajectory is of order of the length of the boundary. And what you would expect in this case. So, and the answer is that it behaves like that. So it has another scaling. Now, since I impose the restriction on the length of the random walk and consider, one can say, double scaling. So n goes to infinity, r goes to infinity under the condition that they are linked together. So and c is constant. So in this case, the deviation above the middle point is not square root but cubic root. Okay. The same question for another shape. So if you have, for instance, triangle, yeah, the same, you stretch. So in this case, you have, of course, diffusive behavior because the trajectory doesn't fill this shape, and so it's more or less the same picture as above. But if you impose the stretching conditions like that, so then again you can ask what will be the span of the trajectory above this point, and the answer is that it's constant in the scaling regime. So you see that if you stretch the trajectory in such a way that it doesn't deviate far away from the boundary, so the answer depends on the curvature and on the structure of on the typical okay, so on the algebraic, which algebraic curve you consider as the surface. Okay, let me try to explain this first using the Zhang-like scaling consideration, and so then I will go in more details. So how we can think about that? So we have stretched trajectory, yeah. So again, the length is proportional to the half of the perimeter. So and then we can do the following. Okay, so it's not so easy to point it. Let us look at the triangle KMNL. Yes, so this triangle. And I will ask the following question. I would like to linearize the shape above, so this curved shape, and I will ask on which distance I can do that. So first, so this is nothing else than just a Pythagore theorem. So x is this distance, r, and vertical distance is r minus y. Y is the small distance as shown in figure. Okay, and now I expand, supposing that y is much smaller than r, and I get this relation, which tells me when I can consider so this curved shape as a flat one, depending on which y I take. Okay, so this is one relation, and the second relation is like that. So because now I have kind of linearized x is linear, above it, the random walk, which is stretched, can be considered as just a random walk where I have a diffusive behavior. Okay, so and now I have two equations. One is first one, and second is this one, and I should solve them consistently. So, and I have this kind of expression from which I can extract the dependence of x on r, and I get the behavior which I'm interested in, and I can now I can generalize slightly this approach, saying that in principle, in this case, I consider I can write this shape in a dimensionless form. So this first expression, x, so this, if I forget about the coefficient, this first expression I can rewrite in this form. Yeah, so it's dimensionless. But also I can generalize it to algebraic curve written in such form. Yeah, instead of having square, here I have some critical exponent which characterizes the shape of the curve. Of course, it's not uniform, but I'm interested in the behavior near the middle point. And if I repeat the same arguments, but replace this expression by this one and keep the second one, because again, I say what is the typical distance above which I can consider the random walk, so this distance as a flat. I end up with the critical exponent for random walk, which replaces this 1/3. It's like that. So look, if I put here eta equal to, so this eta equal to 2, I return again to the standard KPZ type exponent, 1/3. But if I put here 1, which means that I have just cusp, yeah, so eta tends to 1, so the exponent is equal to 0, which reproduces, well, this scaling behavior. Okay, so these are just kind of hand-waving arguments how one can think of how we can try to extract these non-trivial exponents which are distant from the standard random walk exponent. Okay, and now we can again, following Zhang's way of thinking, say the following. We have this picture. If we have constant, if we have just quadratic curve, we have semicircle. So then we can, what we have? We have typical distance on which we can linearize our shape, and this gives me the correlation length. So the blobs, so these elliptic blobs are independent on each other, and so the longitudinal distance is of order of r in power 2/3, and so the width is of order of r in power 1/3. So and therefore we can estimate, namely, the free energy of the path, just saying that we have number of monomers, number of steps, divided by the number of monomers inside the blob. So it's just the number of blobs. So, and in this case, the free energy is proportional to r in power 1/3, and the corresponding Gibbs measure has this kind of behavior. I will later, so this is kind of naive derivation, but later I will confirm this by more, I would say, optimal fluctuational approach, which is more, I would say, representative in some sense. Okay, so this, now why I'm saying about the KPZ type exponent 1/3, because in principle it looks like it deals nothing with the KPZ, but the message is like that. So this comes from the consideration of Ferrari and Spawn, who say the following. Of course, there is a KPZ exponents and even the Parisi-Widom distribution. I'm not talking about Parisi-Widom distribution, it's not here. It's something more simple. But the idea is the following. One can use kind of mean field approach, and this is kind of mean field derivation. In which sense? So this solid shape, you can think of this as in the following way. Suppose that you have viscous walkers. So many of viscous walkers, which form, so which go from this point and end in this point. And then I'm saying the following. All viscous walkers except the final, except the top one, I replace by a kind of field which influences the last walk. So, and I keep it fixed. So what is known is that in average they form the algebraic curve of second order. So, and I replace it by the disk. Yeah, semi-disk or disk, it doesn't matter. The same, of course, is valid if I will continue my disk in this below the axis and consider the closed curve stretched above the disk. Okay. Good. So now I consider this as a kind of mean field derivation of KPZ exponent, which doesn't share the Tracy-Witten distribution, but has distribution which is related to area distribution. So this I will talk about. This I will talk later. Okay. Now this connection. So now I tried to explain this one. Now the connection between RG equation. Let me start with the diffusion equation in the Poincaré upper half plane, and in a moment after this transformation, if I take if I make a change of variables just like that, y is the coordinate in the vertical direction, and x is the in the lateral one. And I make the substitution like that. So, and then I end up with the, so this is very well-known thing, is that Laplace Fourier transform of the diffusion equation in Poincaré upper half plane gives you the Bessel type, the diffusion in radial frame for spectral problem in radial coordinates. So this is just this equation, and for generality, I consider the third type boundary condition. So where G is some kind of arbitrary parameter. Okay, so this is one-to-one correspondence. Either you can talk about the diffusion equation in upper half plane, or you can consider the diffusion equation in above the disk, but you should take care about change of corresponding. So this is the shifted value related to a Laplace transform, and this comes from the Fourier transform. Yeah. Okay. And looking at this equation, you can note that this is nothing else as just Schrödinger equation in the conformally invariant potential, which comes from the metric, which comes from this y. And this problem was extensively studied in the literature, and here are some, of course not all, but at least the key references where this equation was considered. And I will just use the result obtained in the work of Ackermans. It's most convenient language for us. And what one can do, one can apply the rescaling. So we can define the more general potential as shown here. Yeah. So C is the parameter. In our case, C is equal to 2. I consider more general case. So, and we can construct the RG flows in two-dimensional parametric space where these parameters are so this one, and this one. Okay. So, and I'm not repeating. I can find everything in the corresponding references. Just schematically, one can make the infinitesimal transformation. So then rescale the corresponding parameters and expand the boundary condition in Taylor series and apply this transformation, infinitesimal transformation, to the diffusion equation, initial one. Finally, one arrives at the one can see that one can derive the beta function, which is invariant with respect to these two transformations, and there are two beta functions. So one associated with this sigma. Sigma, again, let me remind you, is a variable associated with the drift, with the diffusion, and G is considered, one can consider it as a boundary exponent which controls the boundary behavior. So, and the expression for these beta functions, so it's just adopted to our equation, to our diffusion equation, something which is widely known. And then you can see that the first equation, because now C is equal to 2, first equation gives us just constant, yeah, and it's not interesting, so it remains constant for our conformal potential. But the second has non-trivial solution, which can be expressed has explicit expression, so you can solve it. And it has different regimes, depending on which value of sigma with respect to 1/4 you have. So, and there are 3 different regimes. If sigma is less than 1/4, so then 2 fixed points. So, okay, so I forgot to say that these are fixed points of this renormalization flow, renormalization group flow. So, and depending on which value of sigma we have either real distant G plus minus, or they coincide, merge, or they are complex valued, complex conjugated, and the flow G of Y becomes log periodic. And in this case, this is nothing else as just Efimov type behavior. So, speaking differently, one can say that we solve just so we have this problem, and we solve the spectral problem, or this one, if you wish. We solve the spectral problem for fixed value of G in the fixed boundary conditions in the upper half plane, Lobachevsky upper half plane. So this is the answer. So, and yeah.
I'm a bit dropped. What's the meaning of the fixed
Sorry?
points? What is the meaning of the fixed points? Sorry, I'm not getting that. I'm
sure. For a moment, probably I cannot tell you what is the physical meaning of these points. For me, this is kind of points which signal that there are different type of behavior of the coupling function, of the coupling constant. So if you stay in, so either they are complex or they are real. So if these points are, if you stay in the first regime, so you have not seen this kind of behavior. So let me think during what I'm going to take later. Maybe I will return to that and tell you more in better this. But what I would like to emphasize is that this, what I have said, is related to scaling which has this kind of asymptotics. And so this is the corresponding scale which has this behavior which is typical for BKT type of behavior. And this, so this is known that Efimov type scaling is a signature of BKT type behavior if you have discrete discrete spectrum. Having this kind of asymptotics, you can estimate the gap scale, which behaves like that. So, and this is the typical behavior. Okay. Now, maybe I will just trying to answer your question. I will use another point of view related to this expression, and let me write it like that. So this renormalization group equation I can rewrite in the following way. So first I can introduce so this is nothing special. So I can define the exponential scale like that. Yes, and this equation I can rewrite in the following way. Yes, where I can introduce the potential. I expand this expression, substitute what are G plus minus, and introduce this potential. And now what I can do, I can consider this as a potential, and I can consider the effective action adding the kinetic term, and consider this action and its earlier Lagrange equation. Yes, and in this case, having this kind of equation, I can introduce the time required for the trajectory to cross a nearly flat region of this potential. So this is probably some physical motivation of the point where this G plus and G minus merge. In this case, we are interested in the time for the trajectory to pass this region, and it can be estimated like that. So this is the velocity, and this is, one can say, applying to this kind of action, this is kind of instantaneous action. So, and then if you just compute, if you substitute this potential into this expression, you get nothing else than just pi over square root of sigma minus 1/4. So this is action, and exponentiating it, you get a kind of typical scale related for the time which trajectory needs to pass this flat region near sigma equal to 1/4. So I would say like that. Okay, so let's suppose that we have explored this. Now random walk in Poincaré upper half. So this is more related to with what I started, and this is nothing else, just diffusion equation written in standard frame above the disk. I introduce again the third order boundary condition, and so some initial conditions. The trajectory starts from some point, ends in some other one, and it has at the boundary of a disk, it has this boundary condition and satisfies the radial in polar the diffusion equation in polar coordinates. Okay. So what we can do, we can do the following. We can define the kind of Brownian bridge condition. So it means that if the trajectory, if I have a disk, and the trajectory starts from this point, ends in this point, so runs somehow. So I can fix the point, and at this point I merge two trajectories, one running from this point to this one, and the second running from this point to this one. This is exactly what is shown, what is written here. So at this point I glue two parts of the trajectories. So, and then I can also define the deviation in this direction, just computing the expectation using this omega should be this theta. So, and
Again,
yeah.
Little c is standing for the R0.
Little c is not shown here. Little c is standing for stretching. Is the following. As I said, I have two different parameters. One is related to the length of the trajectory expressed as number of steps, an. And the second is the r, which is radius of the circle. And I consider the following condition. L is equal to CR. Okay, so better to say NA is equal to CR. So therefore, C is the parameter which controls how close the path runs the boundary. And here are the results of numerical results of solution this equation. And the first, so for different boundary conditions. So we take semicircle with boundary condition, third order boundary condition. So this one, and this is the Dirichlet boundary condition. So you see that in log-log scale, we have a straight line, which has exponent close to, so not exactly, but because you should run sufficiently long trajectories, but it's close to 1/3. And if also what we can do, we can compute the distribution function. So this one, yeah. So and this distribution function is well approximated by square of Airy function. I don't know whether one can see here is Airy square, where the corresponding width is r in power 1/3. So typical width is like KPZ, and this is consistent with this exponent, and the same. You see the coincidence of numerics and a square function is very good. So it's almost perfect. So so one can rely on this coincidence. But it's better to go behind. And now what we can do is the following. Again, we explore the connection between the diffusion in radial coordinates and making the change of variables. We can go to the diffusion in upper half plane. So now we go back in opposite direction. We start with the radial diffusion, and we end up with the diffusion in upper half plane. And we can use the WKB approach. So we first define the turning points and expand this function near the turning points. So maybe I will not go into details, but as usually in this situation, we end up with the Airy function. And if you go through the simple computations, we end up with the following result. So the distribution function it's the distribution function corresponds to part of this. Yes. So then it's squared because we merge at this point two trajectories. The fluctuations under this WKB approach share the KPZ type scaling. So, and in our frame, Y0 is the same as the R, the same as the radius of the semi-disk. What I would like to stress, why I consider these two things numerics in radial geometry and WKB in hyperbolic geometry. They merge. What does it mean? In WKB approach, I have not explicitly imposed the condition that I consider stretch trajectory. I just solve within this approximation equation, and I get this kind of KPZ type behavior. But when I go back and I consider just numerically solve the problem of random walk above the curved shape, so then I explicitly impose the condition, explore the condition that my trajectory is stretched. So because they merge, it means that stretching of diffusive path above the convex void in R2 is equivalent to W approach approximation for diffusion in a hyperbolic plane. So that is the message from this point, and now I will try to show you so that this kind of thing and emergence of this kind of exponent has the signature of as a counterpart of the Lifshitz tail. I will try to show. And in order to try to convince you, I can use the optimal fluctuation approach, which is analogous to Balagurov Vaks trapping problem. And let me again return to this problem, but now I consider the disk, and I have a random walk. This is the snapshot of some configuration of the random walk above the disk. And let me again compute the typical span of the trajectory, so delta, above this disk, in the stretched condition.
Why does your random walk, how do you constrain it not to go out?
Because I consider it closed from the very beginning. You can do the following. You can consider a long random walk starting from some point, turning around it, coming to this point, and then you just stretch it. Yeah, you just make it smaller. And in this case, you stay under this kind of condition. So that's. If you ask about the numerics, how one can do that, one can use the conditional distribution first. It's something known, at least for this kind of problem. You can do the following. You can run your trajectory under the condition that you know that at the very end you return to the same point. Okay. So I enclose by the imaginary circle, and I would like to, staying in the optimal fluctuation approach, I have two contributions. One is the confinement part of the free energy to stay for the red trajectory to stay in this narrow region, and this is nothing else as just 1 over delta square, because it can be approximated by just first eigenvalue of the Laplacian in this narrow region. Yes, so this is 1 over delta square is the smallest eigenvalue of the Laplacian in the narrow region, modulus 2 pi. And the second is elongation. So on one hand, I have compression by this, but the second is elongation. This is just Gaussian. Yeah, so this is r plus delta because I try to extend my trajectory and how I lose the stretching energy. So it's just a Gaussian part, which I consider again in the limit when r is much larger than delta. So and this I have, for this I have linear approximation. So and then what I can do, I just can minimize the corresponding free energy, confinement plus stretching. And as you can see, here I have just taking derivative, here I have cube, and here I have nothing, so it's just like that. Yeah? And dependence on the parameter can be explicitly found here. Okay, so but now, with what this should be compared? Forget about this. And let us return to the well-known problem of Balagurov Vaks of one-dimensional array of Poissonian centers. So I have shown this just in the way. So these stripes should be considered separately. I just put them one after another for further consideration. So what do you have? You have just random interval, D1, D2, D3, and in each interval you have a random walk. And then it dies when it touches ends, touches boundaries of the interval. Yeah, so you have zero directly boundary condition. So the question is, what is the survival probability? What is the typical length of the trajectory on which it doesn't survive, on which it doesn't die? And so this is the famous Donsker-Baradan or Balagurov-Vaks problem. So we are interested in the probability that random walk is not trapped at the boundary of random interval till n steps. Typically, these intervals are considered as exponentially distributed if the distribution of points on the line, so you have actually what you have just Poissonian distribution of points on the line, and on each interval you have a random walk. Yeah. So, and in this case, again, we can use the optimal fluctuation of the survival probability, and this is the origin of this Balagurov-Vaks problem. You have, again, two contributions. One is the confinement, so that on some interval, your trajectory is localized, and this is this one. And the second is entropic, is the probability that spontaneously you form a void of given distance. And this is just a logarithm of the distribution function, which is typically exponential. Yeah. So again, two contributions and minimization, and you end up with this stretched exponent form. And now what you can do, you can make inverse Laplace transform and get this kind of, so this is proportional, it's not, this is proportional to typical behavior e to the power 1 minus 1 over square root of s. Yeah.
One more question.
Yeah.
Are these directed random walks?
This is on one dimension. In which sense? Directed random? No, it's not directed random walk. You have interval. You have random walk, which is just a random walk. So
on your cartoons, they always
because this is drawn in time space representation. So if one-dimensional random walk in time runs like that, yeah, always. So this is time, so this is time. And the space variable is this one. So you see it can go forth and back. So it's not
the same as the walk around you.
No, it's not this. No, it's not the same as the walk around. No. No. So, and this is the way how. So, is this something standard? This is the way how the Lifshitz tail can be derived in this optimal fluctuational approach. You do this in, okay, so there are many different ways to do that. Maybe the most transparent is to relate it to the trapping problem. And I will show you explicitly later why it's so. Okay, and now let us compare. On one hand, we have disordered free stretched KPZ exponent and above the convex shape. And in another case, we have just the standard disordered case where we know that there is a Lifshitz tail. So these are in parallels of two different pictures. And now, as you can see, here I have minimization of the free energy, which has this form. Here I have, which is this one. And now I impose stretching conditions. So I make R proportional to N, so it drops off. And I compute the corresponding expectation. So it's proportional to N 1/3. It's proportional to N 1/3. And again, I can compute the probability that I start from that one point and to at this point under the condition that my random walk for the first time touches the boundary reaching this point. So it's survival probability in this case and survival probability in this case.
N on the left-hand side.
This is N is the number of steps in the random walk, stretched random walk, while here N is the number of steps in the standard random walk.
So the right-hand side is time from what you said.
Yes, time. Number of steps can be considered as a time. Yes. Okay. So I'm now making Laplace transform as here. So you end up with the behavior, which is in this case is known that it has Lifshitz. It's known as Lifshitz tail, and this, for instance, consideration. It's not just exactly borrowed, but Nieuwenhuizen and Jean-Marc, so they did something similar. Okay, so and now I would like to end up with this kind of thing, discussing, making kind of turn, discussing how this problem of random walk in Poissonian array of traps is related to hyperbolic geometry and making kind of connection with what about I said from the very beginning. Okay. One can rephrase the problem of random walk in the sequence of intervals in the following way. Suppose that you have a matrix, three-diagonal matrix, where the entries can be either 1 or 0, either 1 or 0. Yes, and the probability, so they are independent, and the probability of having 1 is 1, 0 is 1 minus is p, 1 minus p. And this is just the following. So this is my picture shown there, and here are the following. Is the typical structure of the matrix. So this is the typical block, and you see that once you have a 0, the matrix splits in independent blocks, and the set of eigenvalues in each block is known. This is, I would say, this is rephrasing of what Zhang considered when looked at the vibration of a chain of very heavy and light masses. So then the same problem appears again. Okay, so it's not hard to write explicitly the spectral density of this problem, and it has kind of awful form. And first, let me show you the picture, how it looks like. So this is the snapshots of different spectral densities. So different density of ones. Here you have many ones. You have small number of clusters, and here you have more clusters. Now, some interesting things emerge. We would like to characterize somehow this spectrum. In fact, what we are able to do, we can exactly compute the whole structure. And at first, kind of arguments behind this. We can take, for instance, some sequence which is the limiting shape, so the enveloping curve. So this is sequence consisting of these peaks. Yeah? This one, this, and so on. And let us look where the corresponding peaks emerge. So you see it so that they are given by the sequence of, so these are exact expressions. So this is just zeros of corresponding denominators in the previous expression. Of course, if you decrease p like that, so these the positions of the peaks stay, but the amplitudes becomes lower. And now, how to compute the spectrum? And we end up with the connection with the modular forms, and the naive way of doing that is the following. Let me first look at the red sequence. So there is one-to-one correspondence between this picture and so-called fourth circles. What are fourth circles? You have the interval, and you have two circles of radius 1/2, which touch these boundaries and touch and have one common point here. Yeah. And now what you do, you inscribe here the circles in such a way that again they touch the boundary and the nearest neighbors. So the corresponding curves are shown here in black. So what is known is that if you would like to find where the corresponding where are the positions of corresponding centers, so they form the sequence, and this sequence is one particular example of Fourier sequence. So you have summation. So if you want to obtain, for instance, this 2/3, you should take nearest neighbors, 1 and some nominators and denominators. So to have 2/3, you take 1 plus 3 divided by 2 plus 4. It's 2/3. Yeah, okay. So therefore, each value of corresponding peak is known, and so it's given by Fourier sequence. But we would like to compute the amplitudes. And in order to do that, I will not go into details. We should resum this, but let me end up with the final answer. The corresponding spectral density can be rewritten when you go to the limit of very dense system. So it means that we go to the limit p close to 1. So we have very extended, we have very proliferated picture like that. So in this case, one can express the corresponding spectral density in terms of the following function. So this is the spectral density, and here is the special function which has the following structure. It's logarithm, square root, logarithm of eta is the Dedekind eta function. And it has it is the modular form. So you should make the corresponding the corresponding change of variables, but this is the final expression. Why is so? Why the modular forms emerge here? There is a so-called function which is known as Riemann-Thomas function. So it's known also as raindrop function or popcorn function, which is defined in the following way. So this, you see that it has a signature of the function of the spectral density, but up to change of variables. But how this looks, how this can be constructed. So there is so-called Euclid-Orshar representation. You take first a rectangle, and you put trees of the same height in each point of the lattice, in each point of the lattice. And then what you do, you stay on the interval AB, and you emit the ray from the point O till the top of some tree located in some point. And then you project the corresponding height to the interval AB. So it's like that. Yeah. So you see, if you make the corresponding projection from O to the tree, which is very close, you have a very high peak. If you project something which is far away, so then it's very small. So in this way, you can you see that many things and almost everything depends on the rational, what is the corresponding angle where this tree stays. So, and this function, so I have not that time, but just so this function, so one can generalize slightly this function, saying that, yeah, okay, so I have not defined it very well. So this function is defined in the following way. If x is if x is rational, so then it can be represented as a fraction of two numbers m and n, and which are coprime. So, and then this is the denominator. Otherwise, if it's irrational, it's 0. So that is the definition. And we can slightly generalize this, making just saying that this function is 1 over n in power alpha. So therefore, alpha we can take 2, 3, n. And in this case, we have different shapes. And so if alpha is, for instance, bigger than 1, we have kind of concave shape, and this we have convex shape. And this function, using some manipulations, can be mapped to the following function, which is shown here. So the points are the points computed from the definition of this Riemann-Thomas function, and the lines are the corresponding function f of x, y. So this is x and this is y. So you see that the correspondence is excellent, and as closer you are to the boundary, as smaller is y, so then the more perfect is the correspondence. So now y plays the role of the disorder. Y replaces the value of p of the disorder from this point of view. Now, why I'm talking about that? Because first, because of the following. As I said, I would like to connect. So my way of thinking is like that. I start from KPZ type exponents, and using the optimal fluctuation approach, I tried to link it to the following problem. So I start without disorder, and then at least in the framework of optimal fluctuation approach, this problem is exactly the same as the problem with a disorder, but without any geometry. So there is a kind of, to my point of view, there is a kind of mapping of disorder-free problem with convex geometry or with some non-trivial geometry to the problems with the disorder, at least on the level of expectation values or just kind of mean field, on the mean field level. So, and whether we can go behind. Of course, there is no such complex structure in the convex geometry. But what survives? Whether there is a connection of, whether there is a signature of this kind of behavior in the problems I discussed at the beginning of my talk, saying that there is kind of renormalization group approach for flows in hyperbolic domain or things like that. And to my point of view, the answer is yes, and the connection may be vague for a moment, but I am just sharing with you my thoughts. Is the following. We derived the spectrum of the Randall interval problem in terms of, at least we approximated it using the modular functions, which has SL2Z symmetry, and this is just the Dedekind eta function. So how we can link it with the kind of BKT-like stuff and so on. And my message is the following. So what is, let me show you how it looks like. Just a moment here. So this is the relief of the function I'm discussing. So this, if you wish, at the boundary. So this is the upper half plane. And at the boundary, we have this singular type of behavior, which is mapped on the spectral density of the random cage model with Poissonian distribution. So, but let us stay not on the boundary, but let us try to approach this boundary staying in the whole domain. And let us consider kind of a walk along the geodesics in this full domain. And so then, in some sense, we extend our consideration on the two parametric space. Yeah, when this is our destination, this is our final goal, what we would like to approach. And let us consider the flows in this hyperbolic, in this domain, when we approach this boundary. What physically does it mean? It means that we change the strength of the disorder because this parameter, which controls the distance from the boundary, is related to the strength of the disorder. This is the same picture shown from top view. So, and maybe this is the more representative. So these are some local maxima. These are saddles, and so this is the blue line is the geodesics. So we run along these geodesics when we decrease the strength, when we decrease the disorder, and we decrease the y. Y is 0. We run to this point. So, and let us do that. Let us do the following. So this is my upper half plane, yeah, and it consists on the valley, on complex valley. We do the following. So we stay somewhere here. So this is the disorder which is sufficiently high. So y is small, and we put a heavy mass somewhere in the minima, near 0, and then we adiabatically change the change y. We increase, we decrease the disorder, and we look what is the typical trajectory, which is the image of the path of what is the proliferation of corresponding minima. And this is shown exactly in this picture. So if you don't jump from one minima, you just follow one specific line, you go along specific curve, and you end up with the golden ratio. This can be considered as a kind of renormalization group flow when you adiabatically change when you change the parameter which controls the disorder and doesn't allow to jump from one minimum to another one, you just follow the curve which ends up with the golden ratio. And now this is exactly what is. I will skip these details. This is exactly of what is related in the problem known as phyllotaxis. So you have cylinder, and you have points on the cylinder which are repulsive. So they form the lattice, and then what you do, you just squeeze, you compress your you compress your cylinder and you allow to equilibrate the points in new positions. So this is approach, in the so-called energetic approach to phyllotaxis by Leonid Levitov. And the question is, the answer is that, so the message is the following, so that when you compress continuously the corresponding cylinder, so then the lattice stays, and then that it jumps, it bifurcates to the new geometry, and these bifurcations are characterized by angles which discretely change in during this compression. And the question and the message is that they follow the Fibonacci sequence. Now, looking at our interpretation, so this one, as you see, squeezing of the cylinder means motion along geodesics. So then we pass through the saddle point, which is the bifurcation point, and then we run to the new saddle, and then finally we end up with the Fibonacci golden ratio. And at each bifurcation, we have a local saddle, and we can look at the renormalization group equation near this equation. And this is given by BKT type RJ equation of the type I have shown in the very beginning. So my message is the following. So this sequence of bifurcations, when you go along compression of this lattice on the cylinder, is the sequence of BKT transformation, BKT transitions, geometric BKT transitions, and so from this point of view, there is a kind of maybe vague relation between problem of disordered problem and the problem in which I consider from the very beginning. Again, what is phyllotaxis? So maybe I should remind this.
Okay.
Yeah, yeah. I just 1 minute. So this one. So what is phyllotaxis? So you have a pine or you have a pineapple, and then you compute how many spirals you have on the fruit, and each time it's, so there are some exceptions, but typically there is one Fibonacci number. Typically there is 13. So it's Fibonacci number 1, 2, 3, 5, 8, 13. So, so the question was why so, and Leonid Levitov tried to answer this just using the model, so this model. So I didn't touch the question what happens if the interaction potential between points is asymmetric. Interestingly, in this case, we end up with another renormalization group flow, which ends not with the golden ratio, but with so-called silver ratio. But I don't want to touch this. Okay, so probably I'll stop. Probably I will stop at this point. Just bothering you with some, I would say, eclectic one.
Very naive for you. Is the 1/3 exponent actually exact?
Yes.
Your numerics were not convincing.
Yeah. So this, yes.
And I haven't seen a proof. So,
yeah.
Can you elaborate on this?
Yes, I didn't mention. How to say? I didn't mention that because this is kind of deviation from this. But behind the numerics, which is based on the computation of numerical solution of this thing, we have done the following. In principle, there is a not big deal to solve a radial diffusion equation and extract the asymptotics. But here, the situation is a bit tricky because you should, before you solve the problem, you should take double scaling. You should simultaneously increase the number of steps in the random walk and the radius of the disk. So this double scaling is a bit tricky, but in another paper, which I didn't mention that, we did that using exact counting numerically, and we found exact 1/3. Also, in the framework of mean field approximation, okay, so we can do also the following. I didn't mention that, but the model which can be solved exactly is the following. We have a disk and we have a random walk above it. In order to stretch it, we can impose extra condition, saying that we have a magnetic field in this direction in such a way that this is almost Larmor orbit, but slightly above the solid disk. And in this case, we can pre-inflate our random walk and then allow it, which is already stretched, and then allow it to touch slightly the boundary. And in this case, we reproduce the analytically 1/3.
It's not obvious to me that it doesn't depend on the boundary condition. I mean,
The boundary condition,
it
doesn't depend on the boundary condition. It doesn't depend on the boundary condition. Moreover, here is a kind of interesting phase transition, because there are two kinds of phase transitions. One is the following. You have this parameter C, which is mostly R over N. Changing it, you just increase the number of, so your trajectory starts fluctuating far away from the boundary. And if C is very large, the deviation of the trajectory is far away. And we don't see, so for a moment, we cannot say whether there is a crossover or there is a phase transition, but we see that at large C, there is a Gaussian distribution. So there is a passage from 1/3 to 1/2. This is one point. And second is that we allow our trajectory to penetrate inside the disk with some probability. And in this case, again, we see if the trajectory, if there is no penalty to come inside, so there is no boundary, we have just a fluctuational behavior which is Gaussian. And from this point, this transition is better, is more easy to study, again, numerically, and this, we guess, is of 3rd order.
Do you want the last question, if any? Sergei is in for lunch, so if you want to. Thank you again.